Now shared. Right? So I had intentionally kept this page open. As yesterday, this was the last point we closed. So I intentionally kept this page open for the reason so that you revise again that fluoride, carbonate, and bicarbonate of first group are exceptional in their are exceptional in their behavior as their solubility increases down the group, whereas for all others it is a case of solubility decreases down the group. Correct? Now, this is what we had to start, and I stopped yesterday because this was important. I cannot just go in a rush for this. This is Na2CO3.10H2O, which is commercially, which is known as washing soda. If we dehydrate it completely, if we lose water on heating at about, say, 1000 degrees centigrade or so, it becomes Na2CO3. Totally anhydrous, then it is called soda ash. Okay, it could exist as Na2CO3.H2O, .7H2O, .10H2O. These are different forms of hydrates which are possible for Na2CO3, but you will call washing soda only when it is .10H2O. Okay, Na2CO3 can absorb further water, ठीक, and will form, of course, in presence of further CO2 in presence of water and form NHCO3 bicarbonate. That is possible. Okay. And as it is a salt of weak acid, on adding strong acid, it will release CO2. This is the general information. This page, which is now in front of you, is important for questions. That Na2CO3, as I said, is important. It is called washing soda. तो टेक्सटाइल इंडस्ट्री में, लॉन्ड्री इंडस्ट्री में इसका इंपॉर्टेंस है. अब इस इंपॉर्टेंट कमर्शियली इंपॉर्टेंट कंपाउंड को हम जब लार्ज स्केल पर बनाते हैं तो जो प्रोसेस यूज करते हैं, द प्रोसेस दैट वी यूज फॉर इट्स इंडस्ट्रियल और द कमर्शियल प्रिपरेशन इज कॉल्ड ammonia soda process, or we call it Solvay's process. Either you call it ammonia soda or you call it Solvay's process. Now, please note this very important principle. Why we use this method, I'll conclude in the end. But this principle, that the principle of Solvay process is the low solubility of NaHCO3. And thus, in the entire process, we somehow get this NaHCO3 precipitated. And then we heat that NaHCO3 and form Na2CO3. But this low solubility of NaHCO3 is a very important factor in the preparation of Na2CO3 in ammonia soda process. Okay, it is an important point that we have to notice because there are two questions based on this concept in exemplar and NCERT, which has been again manipulated in different exams. So those two questions will be based on this principle I'll discuss. So now raw material is simple. You take brine. Brine is aqueous solution of NaCl. You have to take ammonia, and limestone. Now, limestone is a very inexpensive form of raw material. Similarly, brine is also not that expensive. The main cost here is of ammonia, which will be recycled. So, uska bhi hame bahut nuksan nahi hoga. What we do is, excuse me, we heat CaCO3. We heat CaCO3 and CaO is formed. Okay, CaCO3 is called limestone, CaO is called lime. CO2 is released. We just do not allow it to go, we store it. We do not use it. We store it, and thus this CO2 is again recycled. So how we use it? This CO2 is passed through a container having aqueous ammonia. So ammonia being basic, first with water is forming ammonium hydroxide. Ammonium hydroxide is a basic solution. CO2 being acidic, these two combine. And as we are passing excess of CO2, whenever you pass excess of CO2, you always have bicarbonate. So you will have ammonium bicarbonate. To this ammonium bicarbonate solution, we add brine. And brine also excess, large amount. Now what happens that the solubility of NaHCO3 is low. So we add large amount of sodium. This sodium, this bicarbonate, they cross the solubility product of NaHCO3. Ammonium chloride being highly soluble, it will remain in the solution and sodium bicarbonate is precipitated. We filter this precipitate, we take it out of the medium and then we heat it in dry state. When you heat it, then bicarbonate is converted to carbonate. CO2 is again released. We do not lose it, we reuse it and take it back to our first stage where CO2 was passed through ammonia container, aqueous ammonia container, we reuse it. Okay, plus we also had CaO as byproduct on heating of CaCO3. We do not throw away this CaO also. We add this CaO into this solution, leftover solution of ammonium chloride. Now CaO in aqueous solution will become COH twice. Okay, strong base will displace weak base from the salt. Ammonia is released. This ammonia again we bring here for recycling. So net if we work with 100% efficiency, that is no loss of any byproduct or anything is done, then you will have a very, very cost effective method of preparation of washing powder. Okay. But yes, this is a theoretical thing that you will be 100% efficient. You will have some losses, but still due to this recycling, things are maintained at lower cost for Na2CO3 dot 10H2O. ठीक, Na2CO3 dot 10H2O industrially prepared by Solvay's process. Raw material, ammonia, you can have limestone. Limestone is ultimately giving us CO and CO2. ठीक? Moving forward, can we use ammonium bicarbonate in place of NaCO3 in baking soda? Answer is no. Because this ammonium bicarbonate on heating will give ammonia, which is poisonous. I want to add one more question. Is it there? No. Can we make K2CO3 by Solvay process? Answer is no. Why? Because the entire principle was based on precipitation of NHCO3. KHCO3 KSP is quite high. It can't be precipitated by addition of KCl. So you cannot prepare K2CO3 by Solvay's process. One more question. What if I add ammonium carbonate and NaCl? Can I get Na2CO3 by this method? Okay, the way it was brine dala. Directly if I had ammonium carbonate and NaCl, can we use this method? What do you say? Can we use this method? Answer is again no. Why answer is no? Because if you use this method, then Na2CO3 and NH4Cl, the two products formed are highly water soluble. And so you won't get any precipitate or you cannot take them out of water. They will remain in the solution and thus you will not have formation of Na2CO3 dot 10H2. I have added this uses also. It is used in water softening, laundering, and cleaning. It is used in manufacturing of glass, soap, borax, caustic soda, used in paper, paint, textile industries, and of course, important reagent in qualitative and quantitative analysis. Next is the nitrates. Nitrates of first group, the important thing that you need to remember, are very stable to heat. Usually all the nitrates on heating, other than first group, on heating decompose to oxide releasing NO2 and O2. But first group nitrates on heating form nitrite releasing O2. But yes, still they are releasing O2. So at high temperature, they can act as oxidizing agent. But definitely at much higher temperature, not that easy. Okay? Their decomposition to oxide is at much, much higher temperature, 800 degrees centigrade, which is not so effective. It always ends up to nitrate and oxygen in the questions in the reactions. Okay? As I have already said, these can act as oxidizing reagent because it liberates oxygen. Moving forward, due to above reaction on heating, first group nitrates are widely used as molten salts as solvents to carry out high temperature oxidation. Okay? They can also act as explosive because anything that on heating solid to gaseous transformation is there. So what happens is the sudden volume change will be there. So if you keep it in a closed container and sudden volume change is involved, so due to that volume expansion, it acts as a explosive. Nitrates are usually explosive. LiNO3 is used for fireworks or firecracker. Remember, it is also used as a red color distress signal. Okay, distress signal, for example, if someone needs some sort of help or something, they will fire a gun. If it is having red color, it is a code that there is someone who needs help out there. So distress signal, usually in sea and all those type of places, this is used. KNO3 is used in gunpowder along with sulfur and charcoal. NNO3 and LiNO3 cannot be used in gunpowder. You can use KNO3, but you cannot use these because due to small cation size, they absorb water. If they'll absorb water from surrounding, your entire gunpowder will be lost. This is the common name of NNO3 called chili saltpeter. Coming to nitrites, nitrites are very stable thermally. They do not decompose at all. Okay. And all of first group nitrites are water soluble. Next is sulfates. Sulfates may one very important compound in this first group is Na2SO4.10H2O, which is known as Glauber's salt. First group sulfates are very stable. Again, they do not decompose on heating. Just remember this particular para, solubility of Na2SO4.10H2O, that is Glauber's salt. It has some peculiar behavior. When crystallized before 32.4 degrees centigrade, then Na2SO4.10H2O is obtained. But above this temperature, anhydrous Na2SO4 is obtained. At 12 degree, Na2SO4.7H2O separates out from saturated Glauber salt solutions. Okay. Next is their reaction with carbon. Only lithium reacts with carbon forming carbides, which are ionic. And this is like the second group tendency. This is more like a calcium acetylide type behavior. So they also react. Okay. Other than first group metals, other first group metals do not react like this directly with carbon. Yes, lithium does, though at high temperature, Li2C2, used in industrial manufacturing of vitamin A. Sodium, if you want to make such compound, you cannot go to carbon directly. You have to use acetylene. And this is basically acid-base reaction, redox, but basically an electropositive metal reacting with protic H, or I should say rather Acidic है, C triple bond CH, right? So this H यहाँ से this is displaced. So I will have C triple bond CH, Na. There is a possibility that other one also displaced. So NaC triple bond CNa, liberating hydrogen gas. ठीक? Anomalous behavior of lithium is certainly questioned and is important. Wherever you are asked about the diagonal relationships, the safest thing to say is their similar charge by size ratio. Charge by size. Why it behaves like magnesium? You say because of similar charge by size, or I can say charge density, they behave similar. Though I will never say same charge density, it is always similar. See, for example, lithium, if I see lithium neutral and lithium and magnesium neutral, there is a difference of 8 picometer. Whereas when they're ions, then the difference becomes 4 picometer. Okay. So charge is 1, size is 76. Like that you will use. Okay? But this is picometer. For entire size, you have to use 4 by 3 pi r cube. Entire surface. Charge density we are talking now. So entire volume, not just 76 by 76 you won't do. So we have already discussed how lithium behaves differently as compared to the group members. It is harder, its MPBP are higher, strongest reducing agent. It forms deliquescent salts, whereas others do not in first group. Lithium hydrogen carbonate do not found in solid state. It is found only in solutions. Unlike other alkali metals, it do not form ethinite. The one here, this is ethinite. Ethinite. It does not form ethinite. It forms carbide of formula Li2C2. Okay, तो इस तरह से behave नहीं कर रहा है. It's a nitrate when heated breaks to oxide NO2 and O2, whereas other first group member nitrite and oxygen is formed. ठीक? LiF and Li2 are comparatively much less soluble because they are far more covalent in nature. ठीक? Coming to its similarity with magnesium. Yes, both of them form nitrites. Oxides दोनों के cannot form superoxide, ठीक, और peroxide. Carbonates जो है they release CO2. LiCl, MgCl2 both are soluble in ethanol. ठीक, both LiCl and MgCl2 are deliquescent and crystallizes from aqueous solution with dot H2O as hydrates. You cannot have anhydrous crystals when you want to crystallize it from its solution. Aqueous solution से अगर आपको इसे crystallize करना है, you cannot crystallize them as anhydrous solution, anhydrous crystals. ठीक? Is that clear? Coming to last is the biological importance of sodium and potassium. I have already underlined the points that you need to just have some idea. Magnesium is basically acting in this ATP functioning, adenosine triphosphate की functioning में ये काम आता है. ठीक? Sodium is having its very important functioning. Memory loss वगैरह जो होता है ना, उसमें सोडियम का बड़ा रोल होता है. ठीक? Both of them ultimately are very important in proper working of our nervous systems or nerve signals. दोनों का ही importance है. There is a very considerable role for them to play. ठीक? So these many level of sodium and potassium should be always maintained in our body. Sometimes, particularly with age, if sodium and potassium levels go very low or low, you will not be able to identify immediately what is happening, but it can take the patients directly to ICU and then finally death. ठीक, recent, but this is not the time. I don't want to scare you, but just few days back, last month, that is in March, I have heard, uh, I would say, 2 death and one finally survived ICU. All three in the range of 50 plus to 70 age group. They behaved similarly and were admitted. Two could not be saved. All three were finally diagnosed with low level of sodium and potassium. One who was like towards 50, lady in Pune, just one of the acquaintances, is saved. And the two who were senior citizens, one in US, other in Mumbai, we lost them. They could not be saved. They told that we are feeling something like this, but the diagnosis was late. So if your senior citizens are telling that I cannot breathe, I am having some issue, please get their ions checked. There are simple tests for sodium and potassium in blood test. Okay. So moving back to our preparation, extraction of sodium metal. Now, though directly it is not important as such, but yes, I just want to share few things that it is very difficult to extract first group, second group metals from their salts or ores because they are highly reactive. Who will reduce them to their metallic state? No element. So practically they can be reduced to their metallic states only by electrolysis. And for sodium, we use something called down cell. Now we cannot use water also to have the solution or to have the electrolyte formation of, electrolysis ke liye we cannot form aqueous solution of salts. Why? Because then again, it is not Na plus which will be reduced to Na. It will be the H plus of water which will be reduced. As we have seen preparation of NaOH. Okay, entire different method. If there is water, Na will not be liberated. So this down cell is the apparatus that we use and is extremely uh, costly, I would say. Take why? Because anode is graphite. Take cathode is cast steel. Electrolyte is solid we are using and melting it. So we have 40% NaCl, 60% CaCl2. Now you may ask why this CaCl2 when we have to prepare sodium, you should have NaCl more, na? Yes, the idea should be there. But what happens if you take pure NaCl? It melts at 803 degrees centigrade. Now, if you have an industrial setup in which in the cell you have to maintain a temperature of 803 degrees centigrade, having a chlorine gas somewhere formed, having sodium metal somewhere formed, and temperatures are so high, okay, it becomes very risky if they will come in contact, and they will come in contact because the apparatus is like that. How can you separate them totally away? So what happens is explosions. Okay? So to avoid, or to rather we cannot avoid, I should have not used the word avoid. We cannot never avoid the risk totally. To minimize the risk is a better statement. Okay? We cannot avoid, we will minimize the risk. And for that, we use this type of mixture, which is acting as a eutectic mixture, bringing the melting point to the minimum possible, that is 600 degrees centigrade. So why we have added CaCl2? To bring down the melting point of NaCl. Now you may say just 200 degree. No, that 203 degree decrease is extremely useful when you are talking about electricity bills, when you are talking of explosions and maintaining the whole apparatus. Okay, so function of CaCl2 is to decrease the melting point of NaCl. Okay, rest I think you can understand by yourself. No problem that if it is a molten NaCl, chlorine will go to anode, sodium will go to cathode, right? And we will keep on removing sodium continuously. We don't want that chlorine comes into contact easily to sodium. Otherwise, it will go back to NaCl. So we'll keep on removing sodium continuously to have a purest possible form of sodium. These are the reaction. Now, as all such industries of making group 1 compounds or elements where chlorine is formed as a byproduct, chlorine itself is commercially important, na? So it is an important byproduct. So we call all such industries as chlor-alkali industry. Okay, so it is one of the important industry, chlor-alkali industry. Clear? Miscellaneous points, just few names which might be useful somewhere. So I have just added here. You can go through it. Why can't we prepare K2CO3 by solvents? I have already told you that KCO3 is much more soluble. So you cannot prepare K2CO3 by solvase method. Clear? So this closes our first group, or I should say alkali. Okay? Moving to second group. Now, as far as second group, members are beryllium, magnesium, calcium, strontium, barium, and radium. Radium is radioactive. General configuration NS2, badhiya. Beryllium and barium both are highly toxic, both B and B. Magnesium and calcium are very essential for human body. And magnesium is also part of chlorophyll. As far as the physical properties of second group are concerned, they are similar to first group. Yes, as compared to first group, they will become relatively harder. Relatively, but not very hard. As compared to first group, they have higher MP and BP, melting point, boiling point, but still quite low. If we compare them to abstract comparison karte, so low. But as compared to first group, high. See? Again, abundance, calcium and magnesium are very abundant. Fifth and sixth most abundant elements on earth. Order of abundance I have written, few O's I have added. Coming to this table from NCERT, please observe carefully. I don't find any such special anomaly here which I need to point out. Almost everything broadly, not exactly, broadly is regular except for density here. Okay, except for density here, there were few hiccups like decreasing, decreasing, again increasing. So this is something. Otherwise, nothing much as such. We don't have to carry any information in our brain regarding melting and boiling point of these metals. So I'm not paying attention to this. Okay. Atomic and ionic radii, normal, nothing to discuss. Metallic character, all are metals, but metallic character will increase down the group. Flame color is very, very important. Beryllium and magnesium due to small size. Small size, so high energy will be required to excite the outermost electron, which is not achieved in the given flame test condition. So they do not give flame test. Rest all, calcium, strontium, and barium. They three give. Again, please exclude radium in general in our conversations as it is radioactive. Okay, so we won't talk of it much. It is 10 or minus 6 or minus 5 ppm. Its availability is also very, very low on Earth. Okay, so calcium is a brick red, strontium is crimson red, barium is apple green. These three are important flame tests that you need to remember from this. And of course, we have already remembered from first group the flame test page that you need to remember. Peak oxidation state is +2. Ionization energy. Just let me go back to this thing. I have done calculation that whenever you talk of going from first to second, ionization energy 1 to 2, of course, 1 to 2, there will be increase in ionization energy. But in first group, this increase is 4 to 5 times. In this, I have done calculation. Now, I don't remember exactly which one where, but I can say from 1.91 to 1.96 times these increase. Someone is 1.91, someone is 1.95, someone is 1.93, like that. This many times. So roughly you can say that the second ionization enthalpy is roughly 2 times of first ionization enthalpy. Okay, whereas in first group, it was 4 to 5 times. So if two consecutive ionization energies are given, properties as are appearing similar. So please check that what is the number of times second ionization energy is given. Using that relation, you can say or you can conclude whether the given metal is from the first group or from the second group of periodic table. Okay? Beryllium has higher value of ionization energy and it usually forms covalent compound. It do not form ions because of very small size. Okay? Coming to hydration energy, very usual expected behavior as we'll go down the group, size increasing, charge remaining same, hydration energy will go on decreasing. Hydration energy decreases down the group. Okay? Yes, as compared to first group, their hydration energy is high. Reason, size is becoming smaller, charge is increasing. Those were uni positive and second group is di positive. So charge density is increasing. So yes, they will show relatively much higher heat of hydration. Is that absolutely clear? So they will show high heat of hydration, but still down the group, it decreases. Beryllium does has the highest heat of hydration in both first group and second group. And therefore, it is always stabilized in water as BeH2O4 2+. If you observe, the type and variety of hydrated salt of second group is much more than in the first group. See, NaCl, it do not form any hydrated version. MgCl2 form hydrated version. This, if you read NCERT block, you will come across some places it is written MgCl2.6H2O. At some places it is written MgCl2.8H2O. Okay, CaCl2 is fixed 6, BaCl2 is 2, that is fine. But MgCl2 has variety. This is because MgCl2 in nature form hydrates from MgCl2.1 to 12. Variety is so large. So both 6 and 8 are okay. Don't confuse that which one should I take. Both are correct. Okay? Due to high affinity of water, CaCl2 is used as a drying agent for gases and several organic compounds. But cannot be used, this is important, but cannot be used for ammonia and alcohol because instead of forming like dehydration karane ki jagah, they themselves form this type of adduct. CaCl2.8 NH3, CaCl2.4 ETOH. So you cannot remove water from them. They are reacting with these from which we wanted to remove water. Okay, so you cannot use them to dehydrate these two type of compounds. This is a very important slide. Please take screenshot if possible, though notes will be given, but still. Solubility of salts. Now this is a general thing. Just focus on it. Solubility of salt decreases down the group. Usually that is what we say. As the size of the cation increases, heat of hydration decreases and the solubility decreases. That is the usual thing. Except fluoride, hydroxide, and oxalate of second group. This is for oxalate of second group. For first group, it is fluoride, carbonate, and bicarbonate. For second group, it is fluoride, hydroxide, and oxalate. Take increases down the group, otherwise decrease. Now, what happens is when you have a solid salt, how the solubility is observed. First, it absorbs lattice energy. You have M2 plus and anion in gaseous form. Then these dissolve in water and they release hydration energy. Now, this lattice energy is absorbed. This hydration energy is released. And the reaction will be more and more visible if the overall exchange is more and more negative. Okay. Now, what happens? Yeah.
It is absolutely not there, but for notes somewhat makes sense. So I'm doing the screen recording stuff. Where is that thing?
Chetna, is it that you are talking to me or? Huh? So we were talking that the salt, it absorbs lattice energy and it released hydration energy. Give me a few seconds to get back. Huh? I was in too much of flow. Hydration energy is released. Okay. Now what happens is taking any one particular anion, considering we are talking only of, say, uh, uh, carbonate or sulfate or anything like this, the lattice energy decreases down the group. Hydration energy also decreases down the group. Why? Both due to increase in their size. Okay, for both this thing is there that due to increase in their size, lattice energy, hydration energy, both are decreasing down the group. But for us, we want lattice energy goes on decreasing and hydrogen energy should go on increasing. No, but both are having an opposite impact, right? Decrease in lattice energy and increase in hydration energy are favorable for solubility. Down the group, both show opposite impact on water solubility. Correct? Usually, the hydration energy decreases more rapidly than lattice, so usually solubility decreases. But with an exception of fluoride, oxalate, and hydroxide, the solubility, the decrease in lattice is more rapid than decrease in hydration energy, so their solubility increases down the group. Please take this page in your mind. This is something Joe, you don't have to cram. You just, if you understand, you can have your own reason framed within seconds that what factor will be referred for their solubility. Okay. Now, once you're done with the solubility, again, it will become very easy for you. Conductivity, yes, they are all good conductors. Solution of metal in liquid ammonia, same as group 1. Nothing new. Same blue solution, same ammoniated electron. If concentration is increased, you will have bronze color. Okay? Due to formation of metal crystal. Everything is same. Nothing new. Okay? Standard oxidation potentials and their reducing property. These are the values that we have. See, M2, M2 plus, if I talk, it is like this. See, E standard from M to M2 plus, it increases from beryllium to barium. Barium is strongest reducing agent, whereas in first group it was lithium. Weaker reducing agent than first group metals. Unke comparison mein they are quite weak. Okay.